Hey everyone, it's Bradley Bush with another algebra video for you. If you're new to my channel, thank you so much for stopping by. If you are not new, thanks for coming back. I really appreciate it. If you like the video or if you find it helpful, please give it a thumbs up, subscribe to the channel, or leave a comment. Today we're talking about writing sums in summation notation. And our to-do list is, first we need to kind of frame the question. We need to show you what a sum is and what we're trying to do in our problems, and then we'll do 5 worked examples. Here we go. Summation notation. So if we have a large sum, and say there happens to be a lot of repetition in each of the terms, we can identify each of the terms as follows. We can have an A1, an A2, an A3, and we're adding all these together up to AN, so they're N terms. But what if we decided we wanted to write these a little more generally, and say we said this was A sub I, this was A sub I, and what if we said all of these were A sub I, and there was enough repetition that we could do this, and we wrote N of these A sub I's. Whoops, that's supposed to be an I. And then what if we said, well, let's just, since they're all A sub I's, let's just write 1, and we'll write one of them, and we'll say I is going to go from 1 to N. 1 is the lower limit, and N is the upper limit of the summation. So it's just a way to write a long sum, taking advantage of the structure of each of the terms, because there's so much similarity. We can just write it in this condensed form. So that's what we're going to do. That's kind of our focus of these examples. We're going to try to find the commonality and then write them in the condensed version. And again, I have the answers over on the left if you want to try them on your own and then see if you get the right answer before you watch the video. All right, so let's look at this first one. A here we have 1 cubed, 2 cubed, 3 cubed, and we can see that continues. That means we have 4 cubed, 5 cubed, 6 cubed, and then we end with 7 cubed. All of these things, so what stays the same? Well, in all of these, we have a cube. So that stays the same. What is it that changes as we go from term to term? The base goes from 1 to 2 to 3 to 4 to 5 to 6 up to 7. So what if we said this was I? The thing that's changing, let's call that I. So I, and the thing that is constant, let's leave there. We'll leave that 3 constant. We'll say this is I cubed. And so let's write I cubed for each of these. I'm going to copy and paste that and see if I can do it quickly. There's another one. There's another one. And here's the one at the end. If we're summing, right, so we've got to have a plus in between. And we have a dot, 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 and then another plus. Now we've kind of written them all alike. We need some notation to cycle through the I 1 through 7. So this is I equals 1. This is I equals 2. This is I equals 3. And up to, this is I equals 7. That would totally work, because the blue I would then just become 1, 2. So this would become 1, this would become 2, this would become 3, which is exactly what we want. In the end, last I would become 7. So that would totally work. That would be perfect. We can rewrite this sum as the sum of I cubed from I equals 1 to 7. Kind of fun, huh? Let's try this next one. B, we have 1 plus 1 over 3 plus 1 over 9 plus 1 over 27 plus 1 over 81. What stays the same? Well, the 1 does. There's a 1 in the numerator of all of these. What changes? The denominator changes. And it looks like there's looks like it changes by factors of 3 because I have 3 here, 3 in the 1/3, I've got 3 in the bottom. In the 1/9, I've got 3 squared. What if we rewrote this? Let's kind of play with this for a second and see if we can rewrite it. What if we said 3, let's say 1/3 to the I. Would that do it? It's kind of hard to see that. And then we have another one, 1/3 to the I plus 1/3 to the I. Let's just look at this. Well, let's keep going first before we look at it. So we have 1/3 to I in all of them. This second one has to be I equals 1. So that means this one to the left has to be 3, or it has to be I equals 0. This has to be I equals 2, I equals 3, and I equals 4 is the last one. This totally works. If we have I equal to 0, then that means this becomes 0, this becomes 1, 3 to the 1, this is 3 squared, this is 3 cubed, which is 27, and this is 3 to the 4th power, which is 81. That totally works. So we can rewrite this as the sum of 1/3 to the I, and I goes from 0 to 4. So notice there's more than one way to write this. There's actually more than one right answer to these. And this is something that I want to highlight. I came up with, and you, as you were following along, we came up with this scenario where it's 1/3 to the I power, and the limits went from 0 to 4. That's perfectly valid. That will reproduce our sum here. But the answer I put over on the left, it's similar, but it's not the same, right? It's the I goes from 1 to 5. So I've shifted my I 1 to the right. Instead of going from 0 to 4, it goes from 1 to 5. And if I do that, I can, but I've got to adjust the exponent. So I've added 1 to my counter, so I've got to subtract 1 in my actual general formula in the exponent. So it's I minus 1 instead of just I in the exponent of the 3. And that's totally valid. Both of these formulas, 1/3 to the I minus 1 going from 1 to 5, and 1/3 to the I going from 0 to 4 for I, those would both reproduce this sum, and they're both correct answers. So it's kind of fun. There's not just one right answer for these. Let's move on to C. Let's look at what we have that is the same. Well, nothing is the same, right? The top goes from 1 to 2 to 3 on up to 14 in integers. And the bottom is 2, 3, 4, and on up to 15 in integers. None of those terms stay the same, but one thing that does remain the same is that the top is always 1 less than the bottom. Or we could say the bottom is always 1 more than the top. So what if we said, let's do I over I plus 1. Would that work? I over I plus 1. And I have I over I plus 1. That would give me 1 bigger in the bottom every time. And I, in this case, would have to start at 1. And that would give me 1 on the top, and 1 plus 1 is 2 in the bottom, which would reproduce our first element. And I equals 2 would give us 2 in the top, and 2 plus 1 and 3 in the bottom. This will work. I equals 3 would give us 3 in the top and 3 plus 1, which is 4 in the bottom. And up here, I equals 14 would give us 14 in the top and 15 in the bottom. So this is what we want. Now notice we could have done this differently. We could have done it I minus 1 in the top and I in the bottom. And we would have had to adjust our counter to be compatible. But there are lots of different ways you can write this, and what we have here would totally work. So this is going to be the sum from I equals 1 to 14 of I over I plus 1. Perfect. Next one. D. D here, let's look at what there, let's just look at the sum and see what we kind of glean from it. We start at 5, and we go to 7, 9, 11. It looks like we're going up by 2 until we get to 31. We start at 5. So if we go up by 2 each time, we've got to have a 2 in there. We've got to have a counter that kind of moves us along in multiples of 2, but somehow our first one has got to land us at 5. So once we get the first one, it'll land us at 5, and then we are adding 2 each time, a multiple of 2, that would totally work. What if we did 2i plus 3? And say I was, what would I have to be in this situation to make 2 times something plus 3 equal 5? I would have to be 1. So that means this next one, I would have to be 2, and I would have to be 3, and then I is 4, 4, 11, and this would go all the way up to I equals 14, and again would have 2i plus, that's 2 times 2, which is 4, plus 3 is 7, perfect. And 2i plus 3, 3 times 2 is 6, plus 3 is 9, perfect. And again, this is not the only way you can do this. You could do this other ways. 2i plus 3, if I is 4, let me rewrite that 4. It seriously needs some help. 4 times 2 is 8, plus 3 is 11. That works. That totally works. 2i plus 3, if I is 14, then 14 times 2 is 28, and add 3, you get 2, 31. So this works. This is the sum from I equals 1 to 14 of 2i plus 3. Wonderful. How about this last one? This is kind of interesting because we've got variables instead of just numbers. So what is common? The A keeps coming. Is the A there? Is there all of the time? Look at the R. The R seems to get bigger, so that seems to be where our counter is. And if we look at this, this is a 1 as the exponent. And we know that r to the 0 is just 1. So if we said this was r to the 0, I think we totally have our answer there. Because we could say a is always there, and then r to the I plus ar to the I plus ar to the I, and we would keep going, ar to the I, and our i's first would be 0, because that would give us r to the 0, which is 1, and the r would disappear, and we would just have a. In our next step, we'd have would have I equals 1, which would just give us r. And next step, I equals 2, which is r squared. And up here we'd have I equals 14. And that would do it. That would totally do it. So we have the sum from I equals 0 to 14 of A R to the I. That's it. Thanks for watching. Hope this was helpful, and hope you have a great day.